given the fact that we have a lot of interest in the sun right now, we got a very active sun. There was a lot of pictures that flew around on the email group that everybody was taking about the big sunspots, and so this talk will be very interesting. So I'll hand it over to Dr. McIntosh here.
I was kind of astonished that 15 months had passed since I spoke with you all. And I was sitting down this afternoon thinking about what I was going to do. And I thought, well, invariably 75% of the people weren't there the first time. So you can bore them for the first time. And then the other 25 were there. And so they're going to get bored. And then they'll maybe, through repetition, they'll maybe pick it up a little bit more. So I've changed the background. It's absolutely nothing to do with the sun, just more to do with a plane coming in on final approach. I take it very literally. And of course, the sun has been cracking off the last, I would say the last month. We've really seen heightened activity as we approach solar. I think we're pretty much at solar max. I don't know if we're at the peak of solar max right now, but we're pretty much there. I think we discussed that the last time I was here based on the slides that I presented. Basically, some of the precursors are going to happen. So we're going to see that with the updates that we're pretty much there. Last week's activity was pretty epic. I hope you all got to see the Northern Lights. Probably they went as far south as you guys. They certainly had them here in Colorado. They had them in New Mexico. Just not so far in latitude from y'all. So I've kind of added a few different elements to this talk at the end to talk about where we're at and more of the components of how we're basically testing this hypothesis at the start. So I'm going to spend about the first 15 to 20 minutes talking about the hypothesis itself and going back to rehashing some of the presentation from 15 months ago. So apologies for those of you who are going to fall asleep. So just in context with you all, Houston, we have a problem. Circa in 2019, it was pretty evident that my peers and I were coming up with a radically different forecast for Sunspot Cycle 25 than was being derived, let's say, out of my peers in the community. So our forecast at the time, 2020, actually the paper was written in early 2019, is the red curve. The historical average since 1750 is the green curve. And my esteemed colleagues responsible for the consensus sunspot forecast is the blue curve. And you can see quite dramatically there's a difference. The difference is the reason why I do a fair amount of these public lectures and unfortunately all over YouTube sometimes. So anyway, so that's where things stood back in early 2021. And so one of the new angles to this, and I'm going to throw in on my very last slide, that there may well indeed be a real world risk associated with adopting such a poor forecast. Okay, so this is the solar cycle consensus forecast that was pushed out in 2020. And you'll notice it says that, it's very Gaussian in shape. Okay, sunspot cycles are not like that, but that's okay. That's not what I'm griping about. July 2025 is solar max. Are we there yet? Oh, that's a year from now. Okay, excellent. And also the peak sunspot, smooth sunspot number is 115. I think we've blown through that. So the question is, are there real world risks associated with this? We'll come back to it a wee bit later. So just to remind you, and you guys as a bunch of astronomers know as much, if not more than I do. And understanding the sun and its activities to do with understanding its magnetism and the patterns of magnetism that it presents is the key to unlocking the billion-dollar question. Unfortunately, what we see on the sun's surface and certainly in the sun's corona is the literal tip of the iceberg. So I'm kind of working off the process that the magnetic fields that we see penetrating through the surface of the sun are buoyant in nature. So basically they have a more buoyancy than the surrounding gas, and they penetrate through the atmosphere. And when you see one pole and another pole, you get a plus and minus magnetic polarity. And then you get two dark pores, right? Because the dark pores suppress convection in the atmosphere, and then they're dark relative to their surroundings. Those of you that are familiar with this spiel know that we've been looking at a much smaller scale of magnetism, called EUV bright points. But to all intents and purposes, these little guys, and you can see them pockmarked all over the corona, are basically little active regions. So it's like the big active regions we see, but in about 100 times smaller. And they're not uniformly distributed over the sun's disk, okay? Interesting story I like to tell here is that my supervisor back in 2002, when I started this work, said, you should track these things, you may find something interesting. We still debate to this day whether or not my supervisor knew what we were going to find. Our hunch is yes, because it turned out that someone had done something similar about 16 years before and found an interesting pattern that doesn't look all that dissimilar from the one that I'm about to disclose. However, a decade later, okay, so we've been tracking this stuff for a decade. So the bottom plot here is latitude distribution or the point density of these EUV bright points, plus or minus 5 degrees around the sun's central meridian every day for 10 years, and you get a pattern like the bottom plot. And I literally had a eureka moment, right? So we noticed something was very wild. And I'm going to draw your attention to a feature that later gets a much funkier name. But if you look in late 1997 or the middle of 2011, you'll notice that at the sun's equator, there are patterns that come in that appear to approach, impinge upon the equator, then all of a sudden they just disappear. Okay? At the same time that those patterns disappear, there is what I would call a blooming of sunspot activity at mid-latitudes. The other thing that we noticed was that these bands, what appear to be bands, overlap each other significantly in time. Now, those of you that are students or savants of the sun will know that there's an epoch where the sun's number of sunspots peaks, right? Solar maximum, where we're at right now. But there's also a trough, and the trough is when the sun can make no spots. But one of the other funky things we noticed was at solar minimum, sunspot minimum, there were 4 of these bands near the sun's equator. And I was like, that's really weird. Why? How's that? Well, it turns out that that's probably pretty critical to the problem, understanding what that is. And apologies for those of you hard of eyesight, but this is literally slides that I developed for the person that was in my job in 2012, right? Just to brief them on what we had found. And this whole idea of these switch-offs at the equator were important, and the fact that we have overlapping systems of bands, and somehow the sunspot cycle was somehow responding to these. In the same email thread, I got a little bit brave. And I said, well, these patterns look pretty linear. I know I'm only seeing one set of bands, but they look pretty linear. And if I was to draw the lines, in fact, it was my 5-year-old at the time that drew the lines, I'm going to say that, I see a cyclic behavior. So, anyway, long story short, the prognostication said, we'll see the sunspots of Sunspot Cycle 25 sometime in the 2019 to 2020 timeframe. And again, we'll see one of these switch-off events near the sun's equator in about the same time frame. So again, this is almost 10 years before it actually happened. Okay, so just to show you, so this is from 2012. Here's the updated plots in 2017. I think we didn't do too badly. And of course, at this point, we're starting to wait. Okay, when is this next event at the equator going to happen? And do we start to see spots? The long answer can be considered in following this, right? So here's now here's now the hemispheric sunspot number on the top, right? So you know that the sunspot number in the southern hemisphere of the sun and the northern hemisphere of the sun is not the same. It's a bit like the hurricane number or the tropical cyclone number. They're not always the same above and below the equator, etc., right? So the sun has the same kind of phenomenology. Two kind of cool things to notice here, of course, is the wild hemispheric asymmetries, especially in cycle 24 to the right-hand side, where the northern hemisphere peaked in 2012 and the southern hemisphere peaked in 2014. That's a fairly extreme case. But also the idea of these vertical dashed lines. The vertical dashed lines in these plots are, of course, the times at which what we implied were magnetic bands near the sun's equator basically died. When they die, activity springs to life at mid-latitudes. The spatial pattern wasn't really new, I guess we found out eventually, was that in 1988, there's a Nature paper talking about this extended solar cycle. Where we jump to is that the extended solar cycle really is the sun's 22-year magnetic activity cycle. So this is the Hale cycle. And subsequently, we have verified that that is the case. So what we're really looking at is the sun's magnetic 22-year cycle. So here's just a lovely little animation driven by our data. So you see the sunspot positions as a function of latitude and time. I've also shown the positions of filaments, actually prominences, no, they're filaments, as green dots on that curve, and you can see that they largely trace the neutral lines between the positive and negative magnetic fields. And again, on the right-hand side, you see the corresponding static picture. So like a butterfly diagram, you can see that the wings of the butterfly are now don't just end at 35 degrees latitude, they go all the way up to apparently 55 degrees latitude, and much further back in time. In fact, starting their journey towards the equator, interestingly enough, at sunspot maximum in that hemisphere. Something that maybe someone can follow up on later, because that's going to be a point of where we're going to be when I come back a year from now and talk to you about Sunspot Cycle 26, right? So anyway, as I said, the end of a Hale cycle is very abrupt. So when these bands impinge upon the equator, we call this event the terminator. It's basically just the termination of a Hale cycle, but it also has some pretty epic connotations if you want to use cheesy graphics to put lots of pictures of Arnold Schwarzenegger all over everything. And basically what happens is that at the sun's equator, the magnetic fields that are impinged upon there basically annihilate one another. They just disappear. Within one rotation, there or thereabouts, activity at mid-latitudes just absolutely springs to life. And that's a staggering kind of thing, that on an object as large and as complex as the sun, that activity can change within one rotation significantly. Global activity changes. So I'm just still recapping here. So we've got this hypothesis that Hale magnetic cycles overlap. And furthermore, they don't just overlap with one another, they interact. And I'll show you that in a little minute. They have regular starts at high latitudes. So this idea of 55 degrees, another thing to probe on later on. The migration time to the equator is variable. It goes anywhere from 16 years to 21 years, which is a huge amount of variability. But that's why the sunspot cycle isn't completely regular at 11 years. Longitude is very important. I haven't showed anything to do with longitude at this point. I thought I would take it out because I think it just gets complicated. And the interaction is not always the same between the bands, but we can track it, which is interesting. The interaction of the Hale cycle bands shapes the evolution of the sunspot cycle, including its amplitude. And so if you're trying to play that million-dollar question of guess the amplitude of the sunspot cycle, well, great, this may help. The other thing that it can do is actually help you understand the shape of the sunspot cycle. And so we've kind of brazenly moved on from amplitude to worrying about shape. And I'll get to that a little bit later on in my update. So up to this date, we'd basically were terminator events. And then we did a study of data going back to 1860, and we found another 10. So in the bottom plot here, we've basically identified 14 yellow diamonds. These are the terminator events that have been determined from observational data. If you wanted to make this into an algorithm and go back and look through the sunspot numbers yourself, and you can do this if you want, you can grab yourself a sunspot cycle record. So in the top plot, it's basically the monthly sunspot number. Probably pretty wise to do a trend subtraction. So this is a 40-year, what's a technique, a statistic called R. Lewis statistic. 40-year window is the blue curve, and when you take the blue curve away from the red curve, you get panel B. When you apply a Hilbert transform to panel B, you get panels C and D. So the nice thing about Hilbert transform is that it allows you to deal with non-stationary time series like the sunspot number, and that's actually a much better thing to do than a Fourier transform, because a Fourier transform implies that the phase of the signal is constantly fixed, and that is absolutely categorically not true with sunspots. Okay, so you see the amplitude function is panel C, and the phase function is panel D. And so the terminator events themselves are, in this presentation, are the zero crossings of the phase function. They also coincide with rapid increases in the, actually that's the maxima in the amplitude function. So you can see that our observationally determined yellow diamonds correspond very well with zero crossings to within astronomical tolerance. Another interesting point that I always like here is if you go back to the Dalton minimum in 1800, and then you also contrast with the peak of activity in 1950, you can see that the terminator separation in the Dalton minimum, the terminator is very separated, then the amplitudes are very low. But when you get to the peak of activity in 1915, cycle 19, the terminators become compressed in time. And so you get these high amplitude things. So that maybe hints at a relationship. And to go after that relationship, we do two kind of experiments. So if I look at my, because my hunch is that the sunspot number, the upcoming sunspot number, is somehow determined by the interplay of the Hale cycles, and that the terminator separation is actually some kind of measure of how much one Hale cycle is eating into the next one. Okay, because it's basically a big interference pattern, and the longer the separation, the lower the number of sunspots I can make. That's the premise. So you do an experiment, you look at the sunspot number between the two, and then the upcoming sunspot number. So experiment 1, experiment 2. And in experiment 1, where you're looking at the sunspot number between the two terminators, there's 0, right? There's no predictability there. It's just random. You might as well just pick the average, and it's always going to be right. However, when I look at the upcoming cycle strength compared to the separation, you get a beautiful linear relationship. And actually, interestingly enough, cycle 24 down there at 13, almost 13 years terminator separation is pretty epic, because nobody could predict its amplitude, but this method would predict it perfectly. The other interesting parts are cycles 5 and 6 down there at the very right-hand side. Those are part of the Dalton minimum. And you can see the very extreme terminator separations there. I mean, 15 and a half years is quite some time. In fact, there's old stories out there that folks thought there's lots of papers in the literature talking about that cycle 5, that there's actually a missing sunspot cycle between 4 and 5, right? Because it's so long. But that's guff. Anyway, so sorry, I'm talking real quick. I'm trying to get through the preamble. So we can observe the progression of Hale cycles. Data seems to support that the concept that Hale cycles interact to shape, modulate and shape sunspot cycles. We've identified a key feature of the Hale cycle, and it's their death. And we've established that that seems to be some kind of precursor. The separation of those is a precursor of upcoming field strength. Now, as of 2019, early 2020, that forecast was at 190 plus or minus 20. Monthly smooth sunspot number. Okay. We've got to wait for the terminator to happen, but that seems reasonable. But also the problem is there's a very fundamental problem in all of this, is that the method, the methodology we're talking about, how the sun works, is not what's in the textbooks. Those large-scale magnetic fields do not play with one another in our conventional models. Okay, they're completely passive to one another. And we are completely the opposite. We strongly interact with one another. So it's a complete diametrically opposite physical concept. So moving on, I showed you this plot a year ago, but there's the Terminator event. It finally arrived on the 13th of December, 2021, after 2 false starts. One of the false starts being election day on 2020, no comment, and another false start in the middle of 2021. But finally, the Terminator arrived December 13th, and you can see that the Sunspot Cycle hasn't looked back since. For context, this is the plot as of yesterday. You can see the 3 sunspots, the 3 Terminators that have happened in the current epoch, or at least since I've been working on solar physics. So 1997, 2011, and then of course 2021 into 22. And you can see the response of the mid-latitudes at the same time. I don't think we're crazy. But that meant that we had to adjust our forecast because instead of it being 9.5 years separation as we originally anticipated, it was 10.75 years. And so it's very close to the average. But that meant that Sunspot Cycle 25 was going to be very close to average too, which was a great disappointment to all the ham radio people, I should say. And if any of you are ham radio people, I really apologize. So again, as of 2020, the data looked like this. Oop, I'm losing my thing here. Hold on. I stretched it too far behind my screen. How are we doing? Is it looking okay? Fair about how these plots move around, they rescale a little bit, but this is the most current plot. And you can see that while we had a dip between between August and March, it's starting to pick back up again. Again, this is where we talked last time. So the Sunspot Cycle was tracing our forecast pretty well and was definitely deviating already from the consensus forecast. Here it is as of this afternoon, and you can see that the green data is past daily data. The red data up there is the current daily data. So the data for May 2024 are in red, and you can see it's coming back into that kind of red zone. So our forecast is still, I would say, holding very strong, considering that nobody's been able to do it before. So I would say we're doing okay. And it's certainly not, at this point, at least, adhering to the blue curve. The blue curve is very much the lower bound of anything that we see. Last time around, we talked a little bit also about the polar reversal and the time of solar maximum. This is a plot that we submitted for publication 2.5 years ago. You can see that it hasn't filled in yet. That's because I'm going to show you. Well, the polar coronal holes have disappeared, which means that the sun's magnetic pole is in the process of reversing, which means that the solar maximum is upon us. And if you're worried, if you go out there and look at polar magnetic fields at all, well, let's see if I can make that disappear. No, it won't let me make it disappear. You can see here's the Wilcox Solar Observatory polar field measurements, and effectively both poles are at 0 at this point. And so the polar coronal holes have closed and reversal is ongoing. Okay, so now we're entering into some relatively new content. Well, it's not really, but I hadn't showed you it before. So on top of doing this kind of just looking at amplitude, we decided that we were going to look at statistically, because it seemed like the hail cycle was a robust repeating event through the data. So all we're looking at here, you see the green boxes that scan across the data set. They are centered on the terminator events, and they're plus or minus 11 years in length. And all I'm doing is scanning across the data, and the panel at the bottom that's evolving is the superposed epoch analysis of the sunspot data. So you can see that it's actually very stable in the terminator time set. In fact, you'll see when it gets to, if I can see if I can pause it at the right place. Right, so that's every sunspot in time. Doesn't that look beautiful? And the next one, that's the average. So you can see that the number, or the average sunspot distribution, follows beautifully, at least statistically, if you're tracking as a function of hail cycle. It doesn't look that pretty if you go just by solar minimum or solar maximum, I can promise you, right? That means it's statistically relevant and important. And in fact, you can pick up Sunspot Cycle 25's data, and put it on the average, and show that, well, you know, there's a lot of literature and a lot of banter on social media talking about, oh, it's so different. Statistically, the distribution of sunspots is not really different from the average. Okay, but I think that's pretty cool. You may think it's pretty boring, but it's just a confirmation. The other thing you can do with the same analysis, if I let it play again, right, is you can look at just the sunspot number instead of the butterfly diagrams. And you can normalize them all as a function, normalize them all in a function of amplitude and time. So because we're playing around with terminator times, I can reset the length scale to be anything I want. And this time I choose it to be between this terminator and my projection of the next one, which would be the end, so 11 years after the past one. And then I stack up and look at the progression of Sunspot Cycle 25 against the statistical average scaled sunspot number. And the average is the white line, the gray lines are 1 sigma error bars, and the red lines are the data. I think it's doing pretty well. And of course, after May, it's going to be back spot on again. So I think that we've got a pretty robust statistical measurement of the sunspot number. The same process can be repeated for the 10.7 centimeter radial flux. So that's a thing that the hams use a lot, and it's also used to drive models of the sun's thermosphere, or the Earth's thermosphere, where or ionosphere, thermosphere, where a lot of low Earth orbit satellites fly. So it's actually a pretty important thing to try and model. And I think I showed you this last time, but this is exactly the same analysis, but now applied to the F10.7 model. There's a couple of curious things in this plot. I'll draw your attention to that second bump, because if I go back to my statistical average sunspot number, there is no second bump. Okay, very interesting. I don't know what it is. Well, I have a clue, I have a hint, but anyway, I'm going to show you how F10.7 has varied over the same time frame. So this was in July 2022. So the red data are daily data points. The blue data, if you can see it, are the monthly averages. There it was in February of 2024, and there it is today. So you can see that it climbs up and it's plateauing. Does it pick up on the second peak, I wonder? Or is this good enough? So in terms of forecast skill, this forecast is about 80% accurate over the time frame, over the 2 years. Okay. Just to put it in contrast, the variant that was put out there by my peers is about 20%. So if you were using this model to drive models of the upper atmosphere where satellites fly, you're probably in good shape. If you're using the other one, you might be losing millions of dollars. So you remember the animation from earlier on. I've updated it to include the early days of Cycle 25. I think this plot it's a beautiful illustration of what's going on, and it's not been tuned to nothing's changed. Believe it or not, it's just looking at the variation, the statistics, and the various time steps, and going what's going on. So again, I'll reiterate that the 22-year hail cycle is recurrent and robust. Those hail cycle bands have a definitive end. We called it the terminator. The terminator rapidly triggers growth and emergence of magnetism at mid and high latitudes within about 1, maybe 2 solar rotations. So not very long. And it happens, of course, at many longitudes. So it spreads like wildfire, literally. The terminator sees a rapid jump in solar proxies. And that's because the upper atmosphere of the sun experiences very profound changes to very small changes in magnetic field. Our old hypothesis was that the bands of the hail cycle contrive to modulate the sunspot cycle and its amplitude. I think that we're doing okay. At least the initial analysis, we may be just lucky, but it seems to be playing out. Terminator separation is one measure of the interplay of the bands. That is, long terminator separations yield small upcoming cycles and vice versa. Seems like our forecast is on target and solar maximum is here. And I wrote this slide in particular, when was that? April 10th, April 12th. And my phrase then was, watch out, solar activity picks up about a year following solar maximum. It really does. That's when the peak in the flare and the coronal mass ejection rate pick up. So what we saw last week may just be a prelude to what comes in the next year to 18 months. So again, just to illustrate to you all that this isn't really a fluke and that we're seeing a pattern of behavior, I've updated my infographic, and remember that I talked about sunspot minimum being a time when 4 bands interact and cancel one another. That cancellation is broken by the terminator event at the equator. Activity springs to life at mid-latitudes, and so on, and so on, and so on. So what comes next? Yeah, I've advanced in time now. Now I'm playing my bands out to 2035. Actually, 2032. And all I'm doing is a linear progression. I'm not doing anything fancy. I'm just looking at when might I see cycle 26. So right after sunspot maximum, I would anticipate within 6 to 9 months being able to see the early tendrils of the hail cycle that will eventually become sunspot cycle 26. That means that the first spots of sunspot cycle 26 should appear in the 2031 timeframe. Okay. And of course, the terminator for that will be about the same between 2031 and 2032. It could be anywhere in that window, but actually, when we get to 2027, we should be able to tell for pretty closely, or have a very good estimate of when that terminator is going to happen. And I'm not sure what's in the next couple of slides in it that will disclose how that works. Because now we're going to briefly talk about when things switch on, they also switch off, right? And I don't know if I've got anything on this, but this is just to illustrate the present state of things with the sunspot number. And actually, you can follow along for yourself at the URL that I put up there, and I can put it in the chat once I'm done. When I talk about things switching off, you'll have noticed in some of the plots, there's a faint dotted line that follows the terminator event about 5 or 6 years out. Well, it turns out you can conveniently scale the terminator to terminator timescale into fifths. I can't say that tonight, I guess. Need another beer. And that's on plot on the right-hand side. That is that red vertical dashed line. You'll notice it's symmetric around solar minimum, which is actually at 4/5 of a Terminator timescale, right? So it's very weird that this happens. Solar maximum is at 0.2, so 1/5. 2/5 is a interesting thing. 3/5, everything switches off, right? So this is when the flares and CMEs pretty much go away, sunspots pretty much go away, and you enter solar minimum conditions. So sometime in early 28, we should really enter solar minimum conditions as we pass through this gate again. So this is the next big test of our hypothesis, is that right about that time frame, other than the fun that's going to come in the next couple of years, the next window is that when things switch off. And but you know, in the meantime, the fun bit is, of course, that the solar wind keeps going the whole time. In fact, the solar wind completely takes over solar activity. And the difference between 0.4 and 0.6, the solar wind becomes the dominant player. And of course, at solar minimum, it is the dominant player. So it's like if you want to think of it, it's the dark side of solar activity. I didn't realize I'd gone through these so quickly. But remember the question I raised at the start. Are there real world risks associated with adopting the model for Sunspot Cycle 20? Here's an illustration from a satellite provider talking about the amount of drag on their spacecraft, right? So a spacecraft that's flying about 100 kilometers above the Earth. Actually, this one's a circular orbit 500 kilometers above the Earth. And if you had been using the kind of, let's say, the government forecast, you would have lost your spacecraft in early 2022. They would have experienced so much drag, they would have been dragged back into the atmosphere and deorbited. Well, some plucky engineers decided to use our forecast to save their satellites, and they did, and they're very happy about that. So those satellites are still presently in orbit. So it's pretty cool, actually, to have what's pretty experimental science be used for applications so quickly. So we're pretty proud of that. So I didn't realize I could skip through that stuff so fast. I'm sure I glossed over things a little bit too much. So if there are any questions, I'm happy to hear them. And again, sorry I went so quickly. Anyway.
I have a question there, Dr. Scott.
Yes, go ahead.
At the moment, the sunspot latitudes are at 15 degrees. Wouldn't you expect that they would be lower at this point of time if in fact we'd reached solar maximum?
And it's, let me play this guy. It's very much to do with where the hail cycle happens to be dictates where the spots are, right? So this is actually it's actually a fairly steep cycle. So no, I just go by, I really just go by where the hail cycle is. I don't prescribe it. It's weird. My mindset on this has really changed radically over the last decade, right? Because it's like, you know, if you read the textbooks, they'll say, oh, the sunspots at the start of a sunspot cycle always appear at 30 degrees latitude. Well, no, they don't, right? They sometimes appear at 35 degrees. They sometimes appear at 40 degrees.
Yeah, sure. Yeah, yep. There are a lot of outliers, of course. Yeah, but the average. I mean, we've sort of been watching this for a while now, and it just doesn't seem to have been moving.
Yeah, I don't know what's going on. I don't think they've stalled. I think it's just, let me say, a very average cycle.
Yeah,
this is what an average sunspot cycle looks like.
Looks like, yeah, I understand that. But I've also noted that the thermosphere climate index is probably the highest that I've seen. I mean, it is weak compared to, say, the highest reading that it's been, but it's at around 27 at the moment. And I haven't seen that for a while. So I just thought maybe things were starting to pick up in this solar cycle. rather than.
Is that the TCI? Is that Martin
Yeah,
Lundsack's?
TCI, yep.
Yeah, you know, but last week's activity blew the lid off that measurement. So
yeah, I know that. That's true. Yeah, I agree with that. But you know, hopefully that's a foretaste of what we're going to see.
I would love to see it. Sorry, go on.
I was just going to say, it scares me to think that we might be heading down the downslope.
Yeah, you know, I'm a bit too gleeful at that, I guess. But there's, you know, it's this idea of understanding shape. I don't think that there's this idea that there's this thing called the Nevishev gap, right? So it's the difference in time between the sunspot max and the flaring max can be anywhere up to 2 years, right? So it's
so did you actually think that, like, the fields are actually at zero now, are they? And they haven't actually yet.
Effectively, I haven't effectively zero. But that means that they've not completely changed sign. I think one of the hemispheres has kind of used the phraseology dicking around zero.
Yeah, it's
right?
just been going up and down, and just can't work out where it's at the moment. But I actually didn't think they had actually turned. So, Steve, I'm just like an eternal optimist. I'm just hoping against hope in a way that, we're not there yet.
I don't think we're going to be here in a year, right? So I think I think maximum at 25 is wild. So I think we're there, and there may be a second repeat, right? That's the other thing you could get. Yeah. So no, I think that but again, let me see if I can go back. There's this interesting thing, right? So the sunspots didn't have a second repeat. Right, the statistical average of the sunspot doesn't, but this guy does.
Right. Okay.
Right, and this, if you've studied any of to do with the 10.7 centimeter flux, it has 3 different components to it. Right, so there's a basal component. Yeah. There's a chromospheric component and a coronal component. I wonder what's creating that second bump.
Right. Okay.
So this shows you that there's going to be pretty intense activity after solar max.
Right. Yeah. Well, that's usually typical, isn't it? That the cycle does seem to pick up after max has been reached. We're looking at like what length? Are you looking at like a 9 year cycle then, if that's the case?
Well, it depends where you're timing it from.
Okay.
Right. So if you're looking minimum to minimum, it's 9 years, but I don't know what solar minimum means.
No.
Right. Right. Because
it means boredom, I think.
Right. No. So if I go back to, let me go back to here. Right. Hold on. Go back to the very start. Actually, let me go back to the info. Sorry, I'm making everyone sick. Right. So this was my big awakening moment. Right. Let me see if I can find. Where is it? Hold on. Sorry, I could probably switch off and go back to it. Hold on. It's around here somewhere. I promise. Oh, this guy. Okay. All right. My big awakening was this idea that I don't know where the bottom is. Right. I know there's a point statistically where there's been 65 days where the sun makes no spots. But if I know that there's 4 interacting systems that are making that happen, that's not a minimum. It's not anything that's very robust, right? Yeah,
I see. Yeah,
it's subjective, right? And so I actually get into lots of fights with my peers about this, right? Yeah, that it's a very subjective thing. That it's a committee that decides when solar minimum is. It's not the sun.
Yes, I realize that. Yeah.
And so the Terminator event, the end of the Hale cycle, seems to be a far more rational episode, right? It's a physical thing.
Yes. Yeah.
And so if you can go back and catalog them, then maybe comparing, again, I'm one person out of thousands, right? But if you start to use them as a statistical measure, you start to try and understand this. You start to see patterns in the statistics that you couldn't before, right?
Right, yeah.
And that's the whole point of the other stuff. But so it could be, what I put in my forecast here, until I can see cycle 26 bands, I'm going to stick with an average cycle 26.
Right.
Which
okay,
means
yep,
that the terminator separation is 10.86 years.
right, okay, yep.
Right.
Mm.
And then if I
Mm.
see the band slipping, I can adjust it.
Just it, yeah, yeah. It's an ongoing thing, isn't it? It's not like you never really know until it's over, basically.
Correct. But we're hoping that within a year we'll get our first indication of that next 5 years, right? And then it will be a case of tracking it over time to see if it's still following that pattern, right?
Yeah, right.
So
yeah.
it's at least we've got something to go by. We're not just guessing.
No, that's right. Yeah, no, it's good. And thank you for taking the time to sort of go through that.
No problem. It's a great question.
Okay.
Hey, Scott,
Thank
I have
you.
a question. You mentioned how satellite managers, spacecraft managers have a very important interest in your predictions, okay? And to me, it sounds like they're your number one customers for this information on a practical basis. Who would be another practical customer for your predictions besides the satellite managers?
It goes, Bill, it goes kind of everywhere from the aviation community to aviation community, the power grid people, planning infrastructure, especially at high latitudes. That you can get into people that are at the space agencies planning long-term missions. Would you want to get the amount of cosmic rays wrong by a factor of 4? If you were planning to go to Mars, for example, and you've got to figure out how much water you've got to carry, or how deep into the Martian regolith do you need to put your device, right? Yeah, no, this is relevant to a lot of not only short-term things but also long-term planning activities. One of my good friends is did an amazing job and won a huge mission to go study solar flares. The problem is that spacecraft is launching in 2027 or maybe 2028. And so it's going to be sitting kind of dormant for 5 years.
Timing is everything.
Well, they didn't know. We were a bit late to the game in providing this advice, and of course, once you've won, the clock is already ticking, right?
Yeah.
So anyway, and who knows, we might be wrong.
Okay, very interesting, very interesting. You mentioned very quickly aviation. What is the concern of aviation? Are we talking about commercial passenger aviation?
Yeah, radiation doses.
I see. Okay, case closed. I get it. All right, thank you.
Yeah. Events like last weekend, right?
Hello, Scott. Quick question.
Yes.
The solar cycle number 25 is a lot more powerful than expected. Does that have consequences on Earth's climate? Obviously, it should, but I'm kind of interested. Are there people who are at NASA and NOAA interested in your forecast because of that?
All right, it's the climate's devious, right? So even though Sunspot Cycle 25 is high in production, the amount of radiation, so the amount of light that the sun is pushing out is varied only by like 0.1%, right?
Mm-hmm.
So it's a tiny variation over a decade, right? There's the variation in the UV, the extreme ultraviolet, and the X-ray is far more significant, and that can impact the Earth's upper atmosphere. We have no idea how that transports, if it transports down into the troposphere, so places where you would measure climate change, right? Perhaps the more devious thing is something that is not captured in the climate models, right? Or really our understanding of planetary atmospheres is the amount of particles coming into the atmosphere, right? So relativistic galactic cosmic rays, or even solar wind particles precipitating through the poles, right? There's a lot of old analyses about this thing called the global electric circuit that's driven a lot by basically space weather, by the solar wind, right? And the fact that does it have a connection to things like thunderstorms and things like that, lightning. So there are analogous things that appear to correlate, but the causation is very difficult to establish, right? So I danced around your question. Right, but so there are patterns that look very much like there's a solar imprint on weather, right? And if there's a solar imprint on weather, I would say there's probably a solar imprint on climate, but you have to establish how the physics works, right? And there's this little problem with climate models. There's a 5-letter word that starts with C and rhymes with loud. Do you know what that word is? Cloud.
Yes, of course.
They don't do well with clouds.
Yes, they are horrible with clouds. Anyway, my point is, at Dalton minimum, there was a huge freeze, in the northern parts of the European Union.
Well, it was the summer with
things
no
like
sun,
that
right?
happened.
Is that right?
Yeah.
Is that the year with no summer?
Yeah,
Is that what it was
year
called?
Yeah. So there is obviously some correlation, even though the radiation coming from the sun is different only by 0.1 or 0.2%. It obviously had something to do with climate.
Can I show you something wild?
Sure.
All right, I'll show you something wild. Hold on, let me see. Give me a second. I'll try and find it.
Okay.
But I've been looking at this, right? And in fact, I've been looking back at Sunspot Cycle 4, right? Because it's the start of the Dalton minimum.
Right.
And I've been asking myself a few questions. And this is really getting down into the weeds. I've got to find the folder that I have on this stuff. Give me a second.
Okay.
You can't see me scrolling because it's still locked on my screen. But let's see if I can. Where is it? Oh, I know where it is. Okay. This is a paper that I just finished, right? So this is I've not been writing lots of papers of late. So all right, so I'm going to change. Wait me a second to switch my screen over. All right, I'm going to share again.
Okay.
All right, here we go. This is interesting, I promise. It's not a total wild goose chase, right? So you can enjoy the title for now. Okay, so one of the things that we get into was looking at the differences between decadal scale variability and longer scales, right? And I've covered, you'll see some of these figures will be familiar to you, and some that I didn't show that will also be familiar to you. But then I try to look at the longer time scales, right? So I'm getting into things like the Gleisberg cycle, right? I don't know if you've looked at any of that stuff, the 80-year period, or the apparent 80-year period. Well, there's something weird going on, right? So cycle 23 was incredibly long. And it was incredibly long because our hypothesis is that something changed in cycle 23 that impacted cycle 24. The reason that cycle 24 is so weak was because cycle 23 was abnormally long. Okay, and if you go back and look through the time series, you see exactly the same with cycle 4. Right, so the start of the Maunder minimum, start of the Dalton minimum. And if you can see me indicating, I'll zoom in a little bit.
Right.
Look at the shape of cycle 4. Do you
Yeah.
see how it goes down and then it has a knee?
Mm-hmm.
Well, cycle 23 has the same kind of features. And if I go back here, I'll zoom back out. I'll go back into my favorite Hilbert transform again. Okay. So one of the things we noticed when we were analyzing the Hilbert transforms back in the day was this weird thing that a lot of the phase functions were linear, but some cycles had an E. So it would go down at one angle, and then at some point it would break and go at a different angle.
Mm-hmm.
Right? Look at cycle 4. Right?
Yeah.
So it goes down, 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 and then it goes off at a tangent. Right? Cycle 5 is no better. Well, we started thinking, what could do that? And also the knee, here's the hint. The knee in cycle 23 was round about the fall of 2003. Any guesses what happened in the fall of 2003?
No.
The Halloween storms. Right? So massive events, right? A series of massive events. Was that enough to slow down cycle 23? Now, go back in time. So you'll notice that red vertical line, right? The dashed line there, that's the Halloween storms.
Yeah.
You don't have to be a rocket scientist to go back to cycle 4 and see the 2 vertical blue lines.
Yes.
They were two storms of epic magnitude, like probably Carrington-esque, if not worse.
Mm-hmm.
In the late 1789 and early 1793-94. And if you look at the climate record, the El Nino index as it was at the time went through the frickin' roof. Right? At the same time, I don't know if there was also, it's a really third rail science, but you get into things like earthquakes at the same, a lot of volcanic activity at the same time. I don't think those are related. But the interesting thing about the 1790 storms is that the aurorae from those were recorded south of 15 degrees latitude.
Oh, wow.
So I've been on a hunt, right? So looking for low latitude solar flares, low latitude aurorae, and things in ice core samples to try and see if there's a pattern to when those events happened and whether or not they were able of sufficient magnitude to impact the growth of the next sunspot cycle. Because then you've got a situation where the tail is wagging the dog. Right? Right? So, right? It's a feedback loop.
Yes.
So if you destroy a lot of magnetic field, you slow the Hale cycle down. You slow the Hale cycle down, you eat into the growth cycle. If it keeps happening, and the interesting thing, if I can find this plot, see if I can find it. I gotta just scoot through this to quick. It's the most recent one. All right, I'm gonna kill this now. Last time, I promise. I'm almost getting to the end and not boring everyone. Oh, I guess I'm boring everyone, but
sorry if I asked the question, everybody, but I'm keenly interested.
Next time, don't ask any questions. There you go. That's the
not bored.
Sorry, you're not bored?
No. Actually, this is quite interesting.
Oh, so it's okay. It's only quite interesting.
Well, you have to keep in mind that we are a bunch of real propeller heads here.
Yeah.
All right. Well, that's okay.
Nerdies.
So this, there's a famous paper in ice core physics, and I'm not sure how robust this is, right? And back in the day, they were looking at for nitrites in ice core samples as proxies for large geomagnetic storms. Right? So if you look through an ice core sample, you could sample up to 10,000 years worth of geomagnetic activity, right? So this is just a sample of those back to 1740. Right? So you see those, so there's my sunspot number on the top. Hilbert phase function on the bottom. You can see the three events in 1790 into 1789 into 1794. You can see them on the time series. But you can also see that throughout the Dalton minimum, there were a series of significant events. Interestingly enough, after the Dalton minimum, there's one in 1820, and there's no more until nearly the Carrington flare. And what happens is that the activity goes down, and then you're just getting whacked and whacked and whacked and whacked. Then it just settles back to normal again. It's kind of like average. It's weird, right? So ask the next. What's the next question? The next question is: does this work for the Maunder minimum? Right?
Yeah, the famous Maunder minimum.
I'll let you go, Luke.
I guess
so
it
if you
should work.
If you take the same ice core sample record and plot yourself a time frequency plot of when these large geomagnetic events took place, just plot yourself a histogram. I'll let you do that. I've done it. I'm not gonna waste your fun. So, but it's crazy time, because then you're literally saying that the tail is wagging the dog, right? That there's a feedback loop between the Hale cycle and flares taking place on the Hale cycle. It makes sense, but whatever. I'm a heretic. What can I say,
Yeah.
right?
Yeah.
Why is that crazy?
What's that?
Why is that crazy?
Why is it crazy?
Yeah.
Remember how at the very start, Joe, I said that in the conventional models for solar physics, the magnetic fields don't know about one another.
Yeah. Yeah. Well, why? Yeah, I don't know. It seems
Yeah.
like, why shouldn't they?
Yeah. The
Well, it
conventional
makes it-
models may not be right, is all you're saying, which is
Yeah.
what I suspected.
Yeah, it makes the actually a lot more elegant, but to make them not interact makes the numerics very simple. Right? It makes the math relatively simple. I've got to be careful. I'm on YouTube, or being recorded, so it makes the math relatively simple. Whereas when you start to add multi-scale interactions, it gets very complex real fast. Or
All right.
not.
Yep. Thank you.
Great question. Sorry for the rabbit hole.
Maybe it's something to do with cosmic rays being, allowed into the atmosphere rather than being rejected when solar radiation is at max. Is that
Well,
possibility?
if you want to do another homework exercise, go look at the Terminator dates. If you can find them, you should be able to find them. They're published. And compare them to episodes in the El Nino index. And you'll see a pattern.
Okay, Anil, we need a speaker for October. Can you be ready to give that presentation?
Which
Can I be a guest,
presentation?
Todd?
That's Scott's presentation, not mine.
Is this and Neil gets to go and do the homework, and I can get to be a guest? Is that right?
Yes.
No, but I think
yeah.
if you look at that, you'll find something interesting.
Yeah, I'm just being a smart aleck.
Hey, can I ask a stupid question?
Sure, there's no such thing, but go ahead.
I remember reading a long time ago that one hemisphere of the sun has more sunspots than the other. But I was curious if if there's any theory about that, or if that's been disproven now, or there. I was at Stanford, and there was a guy, Bracewell, famous professor on Fourier transforms, and he gave like a seminar. He gave a seminar on Fourier analysis of sunspot numbers, and then he said Well, there's an obvious 1-year periodicity that you can see in the spectrum, and that's garbage because that's an observation effect because it has nothing to do with the sun. And he said that there's that cycle's not actually real in the data. That's obviously just like weather on Earth affecting how many sunspots people see. And
are you ready to see the 1-year period?
And so anyway, I raised my hand and said, no, it's because the sun has a slight tilt to the plane of Earth's orbit, and one hemisphere of the sun has more sunspots than the other. And then he like gave me the worst evil eye a professor ever gave me.
Can you so if you look at the screen again now, if you look at the hemispheric sunspot numbers, there's a very distinct 1-year period in the data. It's not the Earth's atmosphere.
No, but I think it's the sun's tilt with respect to the Earth, and then
no, I mean, okay.
Yeah. So basically, just like the sun sees the Earth present the northern hemisphere, then the southern, then the northern, we see a slight tilting back and forth of the sun because the sun's not quite up with Earth's orbit.
Right, and that's okay until you go into space and you don't have that problem anymore.
So the 1-year periodicity is still there even when you go into space.
Yes.
Oh.
And do you want me to show you where it comes from?
Sure.
Right. Okay. So you're not far wrong, and he was definitely wrong, but you're not far wrong, right? Let me see if I can find this. I
Funny, that Bracewell gave me such an evil look when I asked that question.
I bet. All right. So hold on. Just give me 2 seconds to find this. See, I've got a whole back catalog of nonsense, right? So I pick and choose. So remember how I said that longitude was really important?
Right.
And then I totally skipped over it, right? Because I didn't kind of want to go there. Well, longitude is very, very, very important. And in fact, it's one of the big problems we have with understanding the sun is that we don't capture longitude.
Right?
You mean I'm sorry,
longitude or latitude?
Longitude.
Oh.
Longitude of the sun. Right? So here's a series of plots. Oh, sure. I played this and I'm not sharing it. Hold on a sec. I went 15 steps ahead. Sorry. All right, can you see that now?
Yeah.
So this is out of date. This is 2022, so it's just after the Terminator. So there's a trick in meteorology that you could apply. So when they could first look down on the Earth as a global system, they made incredible inroads into terrestrial meteorology because what they found was that local weather was tied to global weather, right?
Yeah.
So and it was tied through these things called Rossby waves, right? So called after the Swedish physicist that found them, right? And
Okay.
one of the ways you can diagnose Rossby waves in a planetary atmosphere is to use this thing called a Hofmöller diagram, right? So this thing was developed in the late 1940s, and it basically what you're looking at is a ring of longitude at a fixed latitude, right? So you're basically taking the data that I showed you earlier, where it's latitude versus time. Well, now you're looking at longitude versus time.
Oh, okay.
Okay, so these are all right. So the one on the left is the southern hemisphere activity belt. The one in the middle is the equator, and the one on the right is the northern hemispheric activity belt. So it's a range of 10 degrees around those things, and what's basically playing is the evolution of the ring around the sun at those latitudes. Okay, so you can see a lot of, and see the fact that actually you can't see it here, but if you look at the equatorial one, the middle one, can you see that there's a train of activity?
Oh
It
yeah,
follows a diagonal line.
Very
right?
obvious.
So what that means is that actually that the magnetic band that's sitting under there is slowly precessing relative to the sun. So it's moving slightly faster than the sun. right? So, or faster than the rotation rate, which means that it's something that's on the inside of the sun at some prescribed depth, right? Because the rotation rate is different as you go down into the interior, right? So one of the things that we were looking for with the Terminator event, remember how I said it's a longitudinal effect as well?
Mhm.
So this vertical dashed line here is the Terminator at the equator, and you can see that all of a sudden it's there's activity there, then all of a sudden there's nothing, and it spreads over all longitudes. Maybe it's slightly easier to see once time has progressed. So this is early in 2022. Now you can clearly see the Terminator at the equator, right?
Yeah.
Do you see it? It's just like there's nothing there, right? But look at what happens at the activity bands. It pops up, but you start to see these diagonal patterns everywhere.
Yep.
Right? And the diagonal patterns actually are wave numbers. So these are longitudinal waves. And they're longitudinal waves that ride on the Hale cycle system. And they
Cool.
create local pressure imbalance. Remember how I said these things are buoyant? So you can just imagine Nessie sitting at the bottom of the solar ocean, right? And then all of a sudden, one of its humps gets buoyant relative to the shit around it. And it happens at the same range of longitudes on each rotation, but it slightly precesses because it's not at the same rotation rate as what you're measuring, right?
Reminds me in geophysics of people finding that like the core is rotating at a slightly different speed than the mantle is rotating at a slightly different speed than the
exactly.
crest.
And because these are rotating objects, almost all rotating atmospheres have Rossby waves, right? So even the mantle has Rossby waves. In fact, mantle Rossby waves have been studied as the precursors. If you could study the Rossby waves in the Earth's mantle, you could figure out where all the earthquakes were going to be, right? So also for the sun, if you know where all the modes of the Rossby waves are, you can figure out exactly where all the magnetic field's going to appear. Now, puzzle that one. That can be your homework for the November presentation.
I've got enough of my own work.
But anyway, no, it's really devious, but this is why longitude becomes important. And as it stands, we only have one vantage point for the sun. Right? So if you had a string of observatories around the sun, or even 3, 4, 5, 6, you could uniquely map out the Rossby wave number. You could basically do meteorology for the sun.
You can't do
right?
helioseismology?
It's not robust enough on the backside. I mean, on the far side. I can't call it the backside of the sun, even though I really want to.
Okay.
It's a Scottish joke. Sorry.
Oh, okay. Well, and the reason
So
I bring that up partly is actually my professor at Stanford in geophysics, I think, was the one who invented the concept of helioseismology, believe it or not.
Helioseismology is amazing, right? And I studied helioseismology as a grad student, and the far side helioseismology is incredible, but it's not quite
enough for you. Okay.
It's not quite detailed enough, right? So
okay.
I'm an observer, so I actually want to fly around the backside.
Yeah.
Permanently, right? So, but it is a beautiful diagnostic.
Well, make a funding proposal.
Yeah, no, they don't have $4 billion to fund the mission.
So the stereo satellites aren't good enough.
The stereo A is dead.
Oh, they died?
Or stereo B is dead. One of the two.
Oh, I didn't
Yeah,
realize.
no, it died. It died in 2014.
Oh dear. Okay, sorry, I didn't realize that.
So in 2015, we wrote a paper using the combined data from stereo and SDO on the discovery of Rossby waves on the sun.
So it's not
because
stereo or it's mono.
Yeah, it's kind of advanced mono at this point because it's back on the Sun Earth line again. So because they're orbiting. So we do have Solar Orbiter, which is on the backside of the sun right now, but its orbital longitude varies a lot.
Okay.
So Solar Orbiter is very cool, and then actually Solar Orbital got up in 2028. It'll go up to about 35 degrees latitude, and so maybe you'll get a hint at what's going on at the poles.
Yeah. Okay.
So whether the sun has a polar vortex or not. So anyway, good question. Thank you.
Okay.
Is there any others? Is everybody asleep?
No, that was very fascinating.
All right, Jeff, I quit. I retire.
Some are still awake.
Absolutely.
All right. I guess the last question is, when can we have you back?
Well, I guess we should do this in a year, right? Is that
Yeah,
is that
that's
a
right.
preferred cadence?
That's our cycle, I guess.
We've got an annual cycle. Yeah, I'd be happy to come back in a year and demonstrate that we were absolutely wrong.
There we go. You can say, see, I told you so.
Yeah. Yeah, no, I would love to do that. I really enjoy these, and
Yeah.
I love the questions.
Yeah, this has been a great series so far. It'll be good to get a third one.
Would be the last one.
No,
So,
no.
Thank you very much, Scott.
yeah, no, my pleasure, and I hope that Anil goes off and does his homework as the
Dream
professor
on.
told him to. Yeah,
That's a tough-
Absolutely. 'Cause I mean, he's already committed for the
That's a
October
tough
for
one.
the October presentation.
yeah, it's the origins of the Monde Minimum.
You're kidding me.
My journey towards a Nobel Prize. That's what it should title should be. I'll even give you a title.
Good one. Thank you, Scott.
Thanks, Scott.
Thank you very much, guys. Have a great evening, and I will see you in a year.
Okay.
All right. Thank you.
Catch you.